Now let us move on. There is a second part to that question. So again, it's just 39. Uh, I don't know. Maybe I wrote 40 that time. So it's again an operator. Rank of t equals to rank of t square. Or yeah. Right. So then part two of the question asks if the range of t is equal to range of t square, which we already discussed. Okay. And part seems like we have discussed everything about that question already. And then they are asking, yeah, so this will range of t intersection null space of t, is it zero? That's their question. Yes or no? We just said that it is yes, and we applied it also to get a projection right inverse so that it becomes a projection. Right? Correct? So this is it fine? Should we do this? Check, prove this. Okay.
Do it, please.
Sorry.
Do it.
What? We do this?
Yeah.
Okay, but then do you agree to this?
Yes, yes, yes. Equal to
So
B.
it's the same thing, right? Yeah.
Oh, no, no,
Or
no, no.
so you prove this later, and this is just the same as saying it follows from that thing that T is injective on the image of T on TV. Yeah. I mean, I'm saying it like this, but if this is not comfortable, you just translate it quickly in your terms. So this does it, no? Because on TV, if you take some vector TV, here T is injective. So TV cannot be in the null space of T. And that's why this is true. You just check, all of them are equivalent. Okay. And part D, right. Part D is this equal to 0? Is this true or false? We just saw examples, na? Projection operators.
Uh, yes, yes.
Yes, right? So, I mean, this is false, obviously. So you see, these questions are really nothing. I mean, if you really understand the subject, you understand what the thing is, and it's not a big problem. Okay. So just check if this is fine, and if you have some questions to ask around these operators. No questions to ask? Okay. So you see, then let's just understand a bit. Let's just say about the previous thing that we were saying. So you see, these operators are very interesting. Okay, and so there exists phi isomorphism such that T phi is a projection. Okay, this we proved, and you should just check it. You should translate it to matrices. Translate to matrices and see what you get. Okay, you get some interesting. I mean, if you translate this to the language of matrices, you should you should get something nice. Okay. Now, and you also try to do this. So, can someone give me another kind of example of this kind of operator? I mean, it will also be a projection by what we have seen. But when we started to say projections, what we meant is, you understand that you take a space, to take a vector, take a this thing, and you project. The operator will project onto this space, which means it will fix this vector, and take this vector to 0. That kind of thing, correct? So that was one source of examples, and we saw that every example is of that kind. Okay, but can you give me another kind of example? And in fact, those examples will become more interesting if you change, if you no longer this is an operator, then also then actually is the real place to talk about them. You can say anyways, well, that is surjective operators. Well, this is a linear transformation, surjective, right? This satisfies star. Is it fine? Yeah, right. So now you tell me, or you should think about this again for homework, is in this case, what is T composed phi if V equals to W? So V is, you go back to the case where V is equal to W, okay? And now there was a phi which we constructed, which was a projection. So I mean, T phi was a projection, and T was an isomorphism. But if we assume that T is further surjective, then what does this projection become? Okay, and the answer is it becomes the identity map. That is very important. So that basically means that if you take a surjective operator, if you take a surjective, I'm sorry, 1 second. You don't right. So you have done this. Right? In this case, what is T phi? Okay, and the answer would be that it is identity. You don't need it to be an operator. Okay, if it is surjective. So, okay, you see my point, right? What I'm saying is that you take this T, then there is a phi such that this is a projection. That doesn't need T to be V to be equal to that doesn't need W to be equal to V, I suppose. Or does it need? So we have proved this in that case. But if V is not equal to W, in that case, do we need? So it is surjective. No, I mean not surjective, but rank of T equals to rank. Okay, sorry. I mean, yeah, there is a problem, right? It doesn't mix because then T square doesn't make sense. Yeah, that's why I'm also getting confused. Yeah, no issues. So you can just do this simpler exercise. T, yeah. If T is surjective, which is same as injective because it's finite dimensional V and V are same. So if T is surjective, okay, you can note it down, try it. T is surjective, then what is T phi that we have constructed? Okay, that is number one. That you should try. Okay, but then this technique that we have used here, you should use this technique. You can use this technique or otherwise to prove this following, that if T from V to W, so now we no longer can do this T square business, right? But if now T is from V to W, surjective, okay, then this is, I think I should not, this is a baby example. There exists a phi such that T phi is identity. Okay. And the third thing, which is actually a theorem in Artin's book, it's a very basic and very important result. You can actually use it to prove rank nullity theorem. Is a very general looking result. T from V to W, then there exists phi and psi such that uh, hmm, yeah, but that's not what I wanted to say. Yeah, maybe I will frame it this this such that means now we are not assuming anything about the operator. Okay, just an operator. Then there exists then this basically this is possible is a projection. Okay, you can translate it to language of matrices and look at it as row column of things and whatnot. Okay. Projection for some phi and psi. Okay, this probably you already know, and then use it to prove the rank nullity theorem. Okay, you should think about this, find it, try to understand it, prove it. Yeah, so please do this. And in the modules part, when we do modules with whenever we do with Vaishnavi and other, then we will see how this is important in the theory of modules. It's it's crucial in the theory of modules. This kind of uh, condition, or we'll see. Yeah. So yeah, let's move on. Let's do one more problem because I think otherwise it's quite. Then these problems are just similar to each other, quite similar to each other. So I don't really know what to do. Anyone have any problem in mind that we want to do? Yeah. Otherwise, maybe I don't know. We'll stop. Yeah.
Can you just repeat what did you say, because someone just came to my room. Someone just came to my room and I didn't hear what you said.
Oh, okay. No, I'm saying that does about mathematics, about these things.
I really don't know whatever you
Oh,
had said.
okay, cool. Then I'll say something new, maybe. Yeah. So then you do this. I mean, this will serve another source of examples for this kind of thing. So again, you take operator from V to V. Then okay, what I said is that I mean, you should give me some problems to try. Otherwise, this just the jam problems means picking up randomly is. I mean, I've done them quite a bit now, I think. So since quite some time, so they're getting repetitive, right? Problems are quite similar to each other, so you should try the problems, get stuck, and hard problems, and then we should discuss them, right? I think that is better. Otherwise, I'll just discuss, give you this question, and then maybe we'll stop for today. Okay. Right. So this is the linear algebra, but then the matter is this, yeah. Show that there exists some n such that range of t to the n equals range of t. Anyone has encountered this kind of thing? You may have seen Jordan canonical form or this kind of thing. So what happens is this is like a, if you do commutative algebra, you know it's Artinian condition, but just basic linear algebra, what this is saying is very interesting. So it just says that you look at this, and then in general you get this decreasing chain. And the claim is that at some point it will stop. There will come a time when it will stop. Okay. And this is quite easy, right? Is it intuitive? It should stop. Finite dimensional. If finite dimensional, it should stop. I can't just keep decreasing. So this is all right. But then what's the point of this? Yeah. Let n be the smallest such. Okay. Then you show with that for this n, the null space also stops. Maybe n naught is the smallest such. Such means where it stops. And you know that like once it stops, it stops. Is that also correct? Right? Is that correct? Or maybe it's not very obvious, but like, so it's very interesting that it will keep decreasing, and if there is a point where it stops, then it will not decrease anymore, right? So this is just I'm saying that if range of t to the n equals to range of t to the n plus 1, then that should imply that the range of t to the n plus 1 equals to the range of t to the n plus 2. Can you apply rank nullity or something here and see? If let's write it here. If A range of t to the n. So you see, I suppose you can see that this is the same thing as a null space condition. Right? Again, by the same, not the same, but same properties. Right? The range is contained in the range is equal. Now you can compare the null space. The null space of t to the n will be contained, but then the rank nullity shows that it should be equal. Okay, so it's twisting, but still it is not very different. Now we are asking for this. Okay. So you see these properties which we are studying, right? Which is once it stops, the first thing it stops. That's true. That's okay. Once it stops, then it stops. And once it's like equal, then it remains equal. You must pay attention to these things. These are the things which are taken as definitions later in mathematics. And then these will serve as your examples. But I think I'm being stupid. It should follow, right? I think I'm also not able to see. N can be anything. Is this true for is this true for n equal to 0? It is true, right? Because then it just means it's a bijection. N equal to 0 means that the range of t is equal to range of identity. Then it's okay, it's a surjection, which is a bijection in this case. And it's a bijection, then if how much you iterate, it remains a bijection. So n equal to 0, it is true. Okay, maybe you can use induction. I don't know. Right. Okay, let's do it. Yeah, so I will do this. This is fine. Similar to that, right? T is injective on this. Okay. That is why the range of T to the power n does not decrease. Fine. Right. So you are just taking T to the power n, applying, just think of T to the power n as an operator, right? As one operator. So then V to V, right? So you go here and then you look at the image. So this is the image. And then you apply T again. And the range, that would be the range of T to the power n plus 1, but it doesn't decrease. It means that T is injective on this. Injective. Right? You should prove it. This is clear. But then this is same as T is injective on range of T to the n plus 1 because they are same. But now this statement applies to this. Correct? Fine. So it's like that, right? This is equivalent. And then it's just same thing for n plus 1. Right? T is injective on this is the corresponding statement equivalence to this. So it's a trivial thing, but you should check it. Because yeah, so do that for homework. I mean, it's important. I mean, if you pay attention to this, then you will actually come up with, you can actually easily understand the proof of Jordan canonical form, which is the first result in linear algebra. One semester of linear algebra, they proved that in the end, in a normal linear algebra course. But we will see that later. So yeah, that's what I was saying. And at this, so all these things are proved basically. I have given you sketches. Now you should complete it. So this is what we have for today. Maybe I will stop. Okay. I mean, if you study these things, then you should tell me. Then we can. So the directions to go from here is to now prove the Jordan canonical form, if you're interested. And the second is to look at really the infinite dimensional case, which is compact operators. Okay. So yeah, but first you pay attention to these things. Like for example, this t square equal to t, right? I mean, the properties shared by these things are used when you study in algebra, you study idempotents come up. In algebra, semi-group theory, computer science, it comes up everywhere. So these, if you understand these, then that's okay. Yeah, maybe we'll stop here. It's already late. So you see, so the next time, next Tuesday, we will definitely do this, hopefully, right? You should practice, you should try some problems from anywhere. I mean, Vaishnav, if you're also trying like these exam-oriented questions, and any exam, and then it's fun to try. Otherwise, it's the same, just application of what we all, what, okay. And yes,
So, is there any class on Thursday?
yeah, this Thursday, I don't think I can do any class. Okay. But yeah, but as you said, next week, you see, maybe on Sunday, then we can do, right? But I will
Then
inform
I
you.
will come along with the field questions actually.
Sorry?
Field questions. I mean, I have field extension in my chapter, so I need to do some.
You want to study field extensions?
Yeah,
Yeah, then maybe Sunday we can then discuss field extension, right?
Sunday at evening or day.
Yeah, what will be a good time? Maybe
Uh,
day? Is
Evening.
it evening? 8:30?
Yeah.
Vaishnavi, is that, do you want to come? I don't know.
No, Saturday we are having class.
Yeah, that is our
Saturday.
morning present. Yeah, yeah.
Okay.
Sunday,
Okay, in Sunday morning, Sunday morning.
okay, 12:30 or 8:30.
What?
Yeah,
8:30?
8:30. Vaishnavi, is it? I mean, if
AM.
you
8:30
yeah
AM.
yeah,
Yeah.
it's
No
field
problem.
field theory and field extensions. Fine.
Yes.
Yeah.
Yes.
Okay. Yeah. So I mean, even you would have seen if you solve the problems in chapter 2 of Atiyah and McDonald, they have some field theory questions, algebraic closure of a field. They ask you to construct, and that actually they do using ring theory kind of ideas, if I remember. Yeah, it's wonderful. Maybe we can discuss that. I mean, we do field theory is this field and field extension. So we will try to do the field theory and then give an overview and see whatever Arnab has. First, we should do that. And yeah. I don't know much field theory actually. So yeah, field Galva theory, field theory. Galva theory, I do not know much. I wish I would. Galva theory is more useful in number theory, right? Yeah, and maybe we'll talk about it on Sunday. Yeah, but do these exercises, please. Okay, keep the time and then don't. Yeah, like do it. Okay, then I'll go. I'll get dinner. Bye.
Good night.
Bye.